All right, everyone. So this is lab one, errors and error propagation. So we're gonna talk about data analysis and how to approach experimental data, what type of experimental errors and let's say error propagation techniques that we can use to represent our data. Let's say at the end of the experiment. So we know that um, you have already, taken physics class probably or any other science classes where you had to do measurements, and every science class technically has different ways of representing their measurements. So in physics, our important, let's say, part is to do a measurement accurately using all the, let's say, experimental measurement tools that we have provided, because some measurements require different tools. When you're measuring, for example, length of the table, you use a meter stick. When you're measuring a small block, maybe you use a vernier caliper or micrometer caliper. But at the end of the day, most of the time, those measurements uh, are used to calculate another result. So, for example, if you want to find the area of the table, you measure the length, you measure the width, and then you calculate those results, those measurements, right, to get the result, which is the area of the table. All right. So, in this lab, we're going to be talking about different type of techniques, different type of, let's say, um, ways that we can represent our data and how to calculate some of the quantities like average, like uncertainty, or standard deviation, or let's say relative error, or percent difference, and all of those things. So those are the things we're going to be kind of going over in this lecture. All right. So one of the ways I'm gonna do this lecture here is by representing sort of like an object that you might be given in a mechanics class. So let's say to make measurements. For example, let's say you have a cylinder. So let's say you're given a cylinder and you're gonna be asked to measure the dimensions of the cylinder. So there are two couple things we can measure, right? So we can measure the length of the cylinder or height. Let me call this like a length. And then we can also measure the diameter. Okay, so we can also measure the diameter. Again, so most of the time, these measurements will be done by probably a vernier caliper. So vernier caliper measures in centimeters, and you have to, let's say there are two types of vernier calipers. There are digital ones that directly give you the reading, or the analog ones that require a little bit of, um, let's say learning curve to learn how to read that. But we're going to be pretty much talking about in terms of once you take a measurement and things like that. All right, so generally when you take a measurement, you don't just measure it once and then go say, all right, here's my measurement. Because one of the things we do here is we already know, and hopefully you guys already know, that there are errors involved in any measurement. Now, these errors doesn't mean that it's wrong or something like that. So the errors are um, basically things that can arise from, let's say, not being careful when you're measuring, or when there are discrepancy between two or three people when they measure the same thing. So those errors are always part of the lab. Okay, and in a way, uh, there are categories of the errors even. So we can talk about, so like let's say personal errors. We can talk about systematic errors, and then we can also talk about random errors. Right, that means those are the three different types of errors that we can have in an experimental lab. Now, the personal errors are, as I mentioned, in terms of you do the experiment, you don't really, let's say, spend time to accurately make measurements. That means this is, every person does things differently. One person, makes the same measurement multiple times because before recording. Another person will just look at it one time and just record it, right? I've seen that. I've been teaching for many years. I've seen, different people, measuring and taking the measurement differently. So, but this is in terms of personal errors. Could be like, let's say you drop something and you measure the time. Well, this could be, one person is, has better reaction times, right? Let's say because when you let go, you have to start. When it hits the floor, you have to stop. Some people are faster, some people are a little bit slower. And those are the type of, errors that we have. Systematic errors are generally equipment, let's say mistakes or equipment problems. You did not calibrate your equipment, let's say before doing experiments. So that's why a lot of times you need to calibrate your equipment before start making measurements. So for example, if you want to look at objects motion along the straight line, well, you want to make sure that your table is a flat, right? It's a straight. Let's say if there's a little bit of curvature, a little bit of incline, then your measurement will be off. So you want to make sure that your equipment is calibrated correctly, and then systematic errors most of the time can be avoided. Then we have random errors. So the random errors technically are the ones that we're going to be dealing with mostly in this lab one, because of random errors, and even all the other labs. Whenever there's going to be big percent errors and things like that, that's due to the random errors most of the time. So those are in terms of again kind of a combination of maybe personal errors, or let's say some kind of errors that you know are known and unpredictable. During the experiment, again before we had a classroom experiment, right? We would have a group of 4 or 5, and then they would do the experiment where they would rotate the, let's say, measuring an object. So let's say one person will make one measurement, another person will make another measurement. So you can see, right, as a data set, you will have random errors because of the, like some personal errors and things like that. Some were systematic errors because people maybe didn't know how to read the, correctly and things like that. So the random errors, in a way, can be, let's say, observational, and they can be environmental. Okay. So that means, in terms of the when the students are actually observing the measurements, or let's say anything else that can happen. So because one of the things we have here, when you measure, for example, a temperature in the room and it's 20 degrees Celsius, well, maybe a little bit later the temperature would increase, and if you don't measure it, let's say when, let's say, you're doing the experiment, then you're going to be using 20 degrees Celsius when the temperature in the room was actually maybe like 22 degrees Celsius. So those are the type of thing that you have to be dealing with. Now, for example, then, taking into account all of these types of errors, right? So when you're doing an experiment, how to avoid or how to present, right, your experimental data, including these type of errors that are part of the experiment. Well, one of the things we do here is when we make a measurement of, let's say, the diameter, right? So again, we don't measure it once; we measure it, maybe 5 to 10 times, depending on the experiment. And then what you have, you basically have a data set. So we can say, all right, so here's my diameter. Um, Let me do it here like this. Here's my diameter in, let's say, centimeters. And when we measured the ones, it was 1.62 centimeters. But this is going to be then number of trials. So like one, then two, and then maybe like three, four, that. So maybe like gonna do 1.63, 1.65, 1.64, and things like that. And the reason that numbers are going to be slightly different because of the different type of errors that we talk about. So very rarely you're going to have 5, 6 people measuring same thing and they get all the same numbers. Whenever I see a group giving me a data set exactly same numbers, I know they just measured it once and then just copied the same value. All right, so there's almost impossible in a lab with this many, this much precision, right? Let's say up to 2 decimal point precision. You do an experiment and you get the exact same value. All right, so you get this. Then that means as a group you have, let's say 5 measurements of the diameter. What do you do? Well, you don't come to me and say, all right, so these are the values that we have. What you do, you calculate and statistical representation of your measurement. So that means you're gonna do pretty much two types of calculations. One is calculate the average, which equation for the average, let's say when you're using the the value for quantity x. So let's say x is something you're measuring. So the value of the average of this quantity x will be x bar. We put a bar on top. So and then this will be sum of all the measurements of for this quantity. Let's say x1 plus x2 plus x3 plus that, right? And then divided by the n number of measurements. N is the number of trials. That means you have then 1 over n, then sum of when I equals 1 to n x sub I. So basically, the sum of your measurements divided by the number of measurements. So this is known as the average. And generally, this is the best representation of your experimental data. That means, all of those values that you see, right? You are calculating one value that you can, present as your diameter. But one of the things we have here is that also, because of all this, let's say errors involved in our experiment, we can represent what we call standard deviation, or in physics usually we use uncertainty. So let's say I like to call this uncertainty, which is basically your standard deviation. So the standard deviation or uncertainty then can be calculated for this quantity x to represent that um, the values, right? There's this variation in the values. So there's a deviation of your measurement compared to the average. For this calculation, then we in general, our handout shows S sub D, but you can use Greek sigma. So so this is the Greek sigma. So sigma x, for example, standard deviation or sigma x, and this is equals to, for example, you take your first measurement minus the average, and then you square it, plus your second measurement minus the average, then you square it, plus that, and then you divide by n. Some textbooks, for example, might give you n minus 1. Okay, so n minus 1 or n, technically either way is correct. So for our handout, we do just n, and then we have to take the square of this, and let's say kind of write it as a little bit short version of that. So this will be, square root of sum of a equals from 1 to n, this x sub I minus x average square quantity, right? Then divided by n, and all of that inside your square root. All right, so then this is your equation 2. All right, so let me kind of put it like this. So that's for the average, and that's for the uncertainty or standard deviation. That means one of the things we can do here is then when you're presenting your experimental measurement, then you can say, all right, so I have this data. I collected this data for the length, the diameter of the cylinder. And the best value that I can use to represent the diameter value is the average. Here's the average. But because of the those many type of errors in the experiment, this number is not precise. Because of the all the errors involved, this number can be as high as its uncertainty, standard deviation, or this number minus its uncertainty. That means as low as this number minus its uncertainty. So that means this quantity x then can be represented like this: x bar plus minus sigma x. That means, for example, if I'm representing for the diameter, then I can say, all right, so here's the diameter value, and the best I can do here is to calculate its average and then plus minus its uncertainty. Because in a way, what we're doing here is we're saying that the best possible way of presenting data is to give a range of values, possible values. That means, for example, if there's some kind of, the experimental graph of the frequency versus, let's say, the measurement, right? What one thing we'll see is that the peak here is where the x average is, but then your measurement that are fall into this, right, will be plus sigma x and minus sigma x. So technically will be within this region, okay? And generally is known as a Gaussian distribution, where about 68% of your measurement generally fall within this, this region. That means within this range. So any type of measurement, 68% of the measurement, technically or approximately 68%, will always, be within this range of average plus minus uncertainty. All right. So for this type of quantities, then this is how you approach. So find the average and then find the uncertainty, and then you're ready to present. For example, then I can say, all right, so the diameter um, is basically its average, for example, is 1.25 centimeters, then plus minus its uncertainty, and when we calculate, the common rule is to always have just one significant figure for the uncertainty. So let's say maybe 0.02, let's say something like that, zero point zero 0.02 centimeters. So because uncertainty is also, has units, it's the same quantity as, diameter. It's because uncertainty of the diameter. That means this is how you represent your measurement. Best value that we can have is the average 1.625, but there are, uncertainties of plus minus 0.02 centimeters. That means it could be 1.645 or all the way down to 1.6 so 1.645 or 1.605. So, something like that, right? So you're basically giving us a range. All right. Now, one of the things we're going to do here is there are also type of measurement where these equations don't apply. Okay, so when these equations don't apply, for example, if I'm asking for you to give me a volume of this of this cylinder. So again, here's a cylinder, right? Let's say, and I ask you to give me the uh, let's say the volume of the cylinder, right? So let's kind of make it look like the previous cylinder, so something like that, right? So the volume of the cylinder. Well, remember, volume is not something that you can measure, right, directly. It's not something you can measure, so you have to actually calculate that. So it's a derived quantity rather than measured quantity. So here's the volume, which is generally the way you know here is pi r squared times the height or the length, right? But since the radius is half of the diameter, I replace the radius with diameter, so I end up with pi over 4 diameter square times length. So that's the equation for the volume. That means I have an equation to find the volume, even though I can't measure it directly. It's pi over 4 times diameter squared times the length. Now the question here is this. Diameter is a quantity that, I already measured and calculated its average and uncertainty, standard deviation. And let's say there's also length of the cylinder, right? What I can do, I can take the same vernier caliper, measure it, 5 to 10 times, find its average, find its, calculate its uncertainty, right? Using those equation 1 and 2, and I can get this. So L plus sigma L. So let's say it's, I don't know, let's say maybe 5.25 plus minus 0.03 centimeters. So let's say those are the values, right? That means those are the things that I can directly measure and use those equation 1 and 2, right? Those equation 1 and 2 to calculate average and standard deviation for those. Okay, so those are the simplest ones as a measurement. Now, but the volume, for example, is a derived, quantity. It's not measured quantity. It's derived quantity. And I have one equation for that. Now the question is that what quantities do I use to calculate volume? Well, obviously the best possible values I can have, right? Which are the averages. That means I am technically then will be using average diameter and average length. And here's the thing, when I'm calculating this, I'm also getting average volume. That means if I calculate those, I'm going to get average volume quantity, okay? Which I can do that, right? I can say um, pi over 4 times 1.625 centimeters square, then times 5.25 centimeters. And I calculate the value for that. But now I still need to represent this, as an experimental quantity, which is volume in terms of its, average and in terms of its uncertainty. Okay. How do we do that? Well, this sigma is not the same sigma over there. That means we cannot really use that equation for this type of calculation because this one over here is for a derived quantity rather than a measured quantity. So what we're going to do then, we're going to use then this, error propagation, which is, the second part of this experiment. So error propagation which is a technique that allows us to find the, you know, basically the errors involved in the measurements of the, or, in finding the volume. All right. So let's do this then. Before calculating this, before, finding this, I would also like to kind of little go over of partial derivatives. Okay, so here, partial derivatives. Okay, so partial derivatives. And if you take in partial derivatives, good. If not, I'm going to give you a little of, overview of that. Is relatively straightforward. And I'm going to use the examples that, I have in the handout. So it's easy for you to follow. So let's say we have some kind of function where f is equals to a function of f where it is, let's say has multiple variables, f of x, y, and z. All right. So then let's say this quantity was 5x squared y and z cube. Let's say this is what, our function f is. Then one of the things I can do here is if I want to take a derivative, let's say, of something, because for example, we know this, right? So we know that if you have a function of x and this is, 5x squared, then taking the derivative of this f with respect to x is nothing but, let's say 10x, right? So which will be, 2 times 5, then times x. Let's say if if this exponent is n, right? So it's just then you do an n minus 1, so basically 1 like that. All right, so it becomes basically 10x. But what if you have, f of x, 5 times x squared, y, z, and things like that? What do we do then? Well, it's relatively straightforward because, for example, again, taking this function, if I'm taking the derivative, or like let's say partial derivatives, which are presented like this, so partial derivative of f, then with respect to, for example, just x, that means I am treating everything but x as a constant. And the only variable is x. That means this is becomes partial, basically same as, you know, taking this as like a 5y z cube and then doing a derivative of just, x squared. It's pretty much same thing because everything else is a constant in this case. So then I'm going to get 5y z cube, then derivative of x squared just going to give me 2x. Then I can say then this is 10 y z cube then x. So then this will be for my partial derivative of x of f with respect to x. And if I do partial derivative of f with respect to y, then everything that is not a y is a constant. That means 5x squared and z cube, they're constant, so I can remove them and then just becomes the ordinary derivative of f with respect to y, which is basically sorry doing the derivative of just of this y. Okay, I should remove that over there. So that was just like this. All right, so that means it's 5x squared z cube and derivative of the y with respect, derivative of just y with respect to y, right? You just basically, or the derivative of f with respect to y is just pretty much 1. So then this becomes 5, that's pretty much the answer. 5x squared um, z cube. Same way, if I do the derivative of f with respect to z, then everything is treated as constant but z. So then 5x squared y. And then I'm doing the derivative with respect to z, right, of just, a z cubed. So then 5x squared y, and this will be then 3z squared. So then 15x squared y z squared. And that's my partial derivative of the f with respect to z. Okay, right? This is, in a way, the derivative of f with respect to x, partial derivative. This is derivative f with respect to y, and this derivative of f with respect to z. All right, so hopefully you guys are able to follow this. If not, just feel free to come to my avatars and then we can, go over this. All right, so the other thing that I have here is uh, what we call errors, absolute and relative errors. So those are the ones that we're going to be using generally for the um, representing the errors involved in something like volume, like area, like parameter, and things like that. Basically, something that is not direct measurement but derivation, calculations. All right. So we can talk about like absolute and relative error. Okay. Now, one of the things we do here is then let me call about absolute error. Okay. So for this one, we then use delta, Greek delta like this. All right, so see, the sigma is the uncertainty or the standard deviation when you're calculating for a measurement or something that you directly measure, right? Let's say, but the delta is for something that pretty much you are calculating or deriving. All right, so let's say this quantity x is calculation or derivation, so then its absolute error is going to be give me then delta x. Okay, then you can also write it in terms of plus minus this delta x when you talk about, let's say, the reliability of your quantity. Okay, all right, so then this is basically what we call for the absolute error. So check, technically delta x is absolute error, then plus minus means that when you have a value for the, for example, volume, so this will be an average, then plus minus, then delta x. So then that's your volume. Okay. Where because delta x is different from sigma, indicating that delta x is a for a quantity that has been derived rather than measured. All right. So in this particular case, then we can talk about the relative error, which is nothing but uh, ratio of the delta x over x. Okay. So for example, it will be the delta V, delta of volume, right? Absolute error of volume over the volume quantity. Okay. So um, in this case, just a ratio, which a lot of times can be multiplied by 100% to get a percentage. Okay. So for example, you have the volume of, like, let's say 20 plus minus 0.5, let's say cubic meters, right? For example, then 20 is your volume, right? Or average volume, and zero point 0.5 is your then uh, absolute error in volume. Let's say delta V. Okay. So then one you can do like 0.5 over 20, then you get basically in terms of the derivation of this one, right? So, the relative error. So, but a lot of times it's going to give you a fraction. So then you can just basically multiply by 100% to get as a percentage. Okay, sometimes it's easier. And sometimes, let's say if you're given, for example, 20 plus minus 5%, that means, you can just use this reverse engineer to get the, absolute error. Okay, so you can also basically do that. Now, one thing we can do here is if you then calculating the error, then do this calculation of error. So let's say this is for, again, some kind of quantity f, where f equals, f of x, y, z. Because let's say, for example, you have a volume, right? Volume, has two, variables, right? So diameter and, remember the equation I showed you, right? So it's pi over 4, then times diameter squared, then times length. Okay. So that means it depends on diameter and length, right? Volume changes if you have a bigger diameter. Volume changes if you have a, longer length and things like that. So then similar to this, f equals f of x, y, z. All right. So then to calculate the absolute error of this quantity f, let's say delta f, so there's a template equation. There's a template equation which will be then square root of, um, in a way you can think like this. It kind of goes like this. There's initial equation is this is 1 squared, and then this is equals to, then you have a partial derivative of f with respect to x, then times absolute error of in x, this is squared, plus then partial derivative of the f with respect to y times delta y, this all quantity squared, then plus partial derivative of the f with respect to z, then absolute error in z squared. Okay, and then one thing we do here is take the square root of both sides, then you get basically that equation over there. So this equation, again, it's in the handout. So then we can use this equation to calculate, so this is for the absolute error, and then we can also calculate the relative error. So this is absolute error. Okay, and then you can do also the relative error. So the relative error then will be just taking this and divided by, the f, right? Because, absolute error of the quantity divided by the quantity. That's then going to be relative error. That means you just basically take the 1 over f, and this whole thing that we have in a parenthesis. Okay. So then let's see then what we have. For example, remember, if I calculated, those quantities, right? Partial f, partial x, if you remember, I calculated that to be, remember, this is, again, it's in a handout. This was 5yz cubed, then partial f partial y was 5, sorry, so it's 5x squared z cubed, and then partial f partial z was 15x squared y z squared. Okay, so those are the quantities that I have. Now, in terms of then what I have here is this. So if I'm doing then this calculation, delta f over f is equals to square root of, so 1 over f, then I can write it down, right? So it's 5yz cubed, then delta x, this one, both of them squared, remember, so that the template equation over there, right? Then plus partial f partial y, which is then 5x squared z cubed square delta y square, then plus 15x square y z square square sigma z square. Okay. Generally, then one of the things we do here is we would also take this and this 1 over f, right, and incorporate inside. Okay, which in a way means that each term has 1 over f square, and we would then factor it out. That means this is, if I put it inside, then it's going to be 1 over f square, 1 over f square, 1 over f square. Okay, so I can add in something like this. Okay, and you can see, right, if I do this, and then remember the f itself was nothing but 5x squared y z cubed, right? So I can just incorporate those all of them into this and then find the calculation. Okay, so if I substitute for f squared and then cancel everything that can be canceled out, then we can get this equation, square root of 2 sigma x over x squared plus sigma y y squared plus sigma 3 sigma z over z squared. And then we have this equation, and then we can just basically plug in and calculate if you are given the values of x, y, and z. Let's say in this particular case you were not, but if you were given, you can also do this calculation. All right. Now, how about as a last example, we apply what we just learned to our a volume example, right? Volume measurement. So remember, volume was pi over 4 times diameter squared times length. This was then from measurement of diameter, which was for this particular content, though. That means I can say that this is d plus minus. In a way, I can say that let's say this sigma d or delta d are pretty much identical because it represents the error in the measurement, right? Uncertainty measurement. And then L also. So it was average plus minus then delta, delta L. All right. So in this particular example, then, remember, I will be using averages, right, to calculate the average volume. And now how to find the delta V? Well, to find the delta V, then we use this template of propagation of error. That means my equation should require me this delta V over V, right? So the, delta F over F, right? So delta V over V is equals to, then it will be then square root of, remember, my quantity was volume. So then what I need to do here is this partial derivative of the volume with respect to the first measurement, which will be D, and this is squared, and then times delta D squared, then plus partial derivative of the length, sorry, of volume with respect to another measurement, which is then the length square, then sigma L square. So this is basically my equation. And this is 1 over V, right? This is 1 over V. That 1 over V is in both sides. Okay, so this is my equation. And then one thing I can do here is find those partial derivatives. For example, partial derivative of V with respect to D. All right, so let's say, what do we get from here? Well, this is my equation, right? That means if I'm taking that derivative of that equation with respect to D, we're treating everything else as constant. So that means, I have pi over 4L, and then just doing delta V over delta D, where in this case, the only thing I have here is just the D square, right? That means what I will have here is pi over 4 times L, and then the root of D square, right? So that will be then 2D. So those cancel out. So like, let's say it's going to have pi over 2 L times D. That's what I get from taking the partial derivative of the volume with respect to D. Partial derivative of the volume with respect to L. So then pi over 4, that means everything is constant but L this time, right? Then D squared is a constant. Then I have partial L of just L, which just means that I'm going to get pi over 4 D squared, because, derivative of the L with respect to L is just 1. All right. Now I would plug in this into the equation here. So I have then delta V over V is equals to 1 over V, then square root of. So then I have pi over 2 LD squared times sigma D squared, plus then pi over 4 D squared, right? Then sigma L squared. Now I can incorporate 1 over V inside. So then this is 1 over V, 1 over V squared, 1 over V squared, like that, which then allows me to, rewrite partial derivative of V, or so absolute value of V over V is equals to then square root of. See here, all those quantities are squared. So I can, in a way, say it's like this. Is pi over 4 L D, and then sigma D over volume. Volume was pi over 2. Sorry. This is pi over 2. So pi over 4 D square L, right? This was the volume. And this, everything is then squared, right? So I'm basically putting everything together in one parenthesis, where this is the derivative of the V with respect to D, and then the bottom is just the volume square. Okay, so the volume. So then the plus, so I put again pi over 4 diameter square, then put this one inside sigma delta L, then divide by the volume, which is pi over 4 diameter square L, then whole thing is square. Then I can simplify this. See, pi over 4 cancel out. Delta square, d square cancels out. Here, um, pi cancels out, L cancels out, this d cancels out with this one, and then this two cancel with that one, and I have like an extra two over there like that. Okay, which means that my equation becomes delta v over v is equals to square root of 2 times delta d over d square plus delta L over L square. So simplifies to just that. Then once I have values, I can just plug in where the delta D over D is just a relative error for the diameter. Remember, the diameter was a measurement, and I have both D and delta D, right? Same thing with the ratio of length. I have both average and uncertainty. So basically, in this case, sigma L and delta L are basically the same. Sigma D and D are pretty much can be used as the same, and I can just put in and calculate that. All right, so that's it for this. Hopefully, you guys were able to follow what I was doing here with the propagation of error method. So again, you just pretty much a template. You just calculate the partial derivatives, put it in a template, and then just cancel out everything until you just end up with the last expression. All right, guys. So then go ahead and start working on the last page exercises, which we'll be doing in 2 weeks. And if you have any questions, you have this Wednesday and the next Wednesday to come and get help from me during my office hours. All right.